there's enough moisture in the air, it will freeze and form frost. This is exactly what happens in the cooling coils of a mechanical refrigeration system that uses Freon as a refrigerant. There are many other substances that evaporate at such low temperatures that they make good refrigerants. Ammonia is a good refrigerant and is commonly used in commercial ice-making plants. But it isn't considered suitable for Navy use because its fumes are irritating and it is slightly inflammable. Carbon dioxide is a good refrigerant too, also used in industrial systems. But chiefly because of the tremendous size and weight of the equipment needed to handle its high pressures, it isn't used in modern Navy systems. Freon is the refrigerant used in most Navy systems today. It is safe, and the equipment needed to handle it is light and compact. Let's see now just how a mechanical refrigeration system works. Let's trace the flow of the refrigerant in a simplified system. Let's start with the refrigerant in liquid form under pressure. Now let's lead the refrigerant to the first main unit of the system, the thermal expansion valve. The thermal expansion valve is simply a small adjustable opening. As the liquid refrigerant passes through the opening in the valve, it breaks up into a fine spray. At the same time, it enters a space larger than it occupied before. In this larger space, there is less pressure, and the refrigerant expands. This drop in pressure makes it easier for the refrigerant to vaporize or turn into gas. This is the first stage of the refrigeration process, expansion. Now the refrigerant goes on to the next main unit in the system, the evaporator. This is where the cooling takes place. The small particles of liquid refrigerant, with their pressure reduced, now begin to evaporate and turn into gas, absorbing heat from the air and food near the evaporator, just as alcohol absorbed heat from your arm. By the time the refrigerant reaches the end of the evaporator coils, it has absorbed enough heat to be completely vaporized. It is now a warm, low-pressure gas. This is the second stage of the refrigeration process, evaporation. The refrigerant has now done its cooling job, but we can't just pipe it overboard. Not at $1 a pound we can't. So now we have to get the heat out of it and use it over again. To do this, we first lead the refrigerant gas into a compressor. The compressor raises the pressure of the gas, brings it back up to the pressure of the liquid refrigerant we started with. In order to have a continuous flow, 2 or more cylinders are used in the compressor. This, then, is the third stage of the refrigeration process, compression. But the heat has to be taken out of the gas so that it will turn to liquid. So the warm, high-pressure gas is led into the next main unit of the system, the condenser. So that the gas will lose its heat faster, cold seawater is piped into a series of tubes inside the condenser. The warm refrigerant gas circulates over the cold tubes. The cold seawater absorbs heat from the warm gas. When the gas is cooled, it turns to liquid. The liquid refrigerant, still at high pressure of course, flows from the condenser back to the main supply or receiver, then onto the thermal expansion valve and on through the system as before. This is the refrigeration cycle. How about watching it again, quickly? The high-pressure liquid refrigerant flows into the thermal expansion valve. It breaks up into small particles and expands into a larger space, becoming a low-pressure liquid. It then goes into the evaporator, where it evaporates and absorbs heat. It is now a gas, still at low pressure. Next, it passes into the compressor, where its pressure is raised again to the original pressure of the liquid refrigerant. It comes out as a hot, high-pressure gas. Then it goes into the condenser, where it gives up its heat and becomes a liquid at high pressure. It then flows back to the receiver and onto the thermal expansion valve for another cycle. We can readily see that part of the system works under low pressure and part of it under high pressure. We can call these parts the low side and the high side. The thermal expansion valve and the evaporator are on the low side, while the compressor, condenser, and receiver are on the high side. Now that you've seen this simplified system, let's trace the flow of refrigerant through an actual refrigeration system. This is typical submarine equipment. It is set up this way for instruction purposes. On board, of course, it is crowded into much smaller space. That's why it is especially important to know every part of the system and what it does. And by the way, this is a 2-ton system according to the Navy rating. And this might be a good place to explain what that means. Tonnage rating is a measure of the refrigerating capacity of the system, the amount of work it does. It is based on the number of BTUs the system absorbs per hour. Maybe you'd like to know where this rating comes from. Well, it's all based on a ton of ice. Since 1 ton of ice in melting absorbs 12,000 BTUs per hour, a refrigeration plant that absorbs this amount of heat is rated as a 1-ton system. Therefore, a 2-ton system, such as this one, would absorb 24,000 BTUs per hour. If this system were to be used for air conditioning, it would not have exactly the same rating. That's because it's slightly different operating conditions. Now, let's go ahead and trace the flow of refrigerant and see what the parts of the system actually look like. This is the thermal expansion valve, where the high-pressure liquid refrigerant breaks up into small particles and expands, coming out as a low-pressure liquid and going into the evaporator. Here, the refrigerant evaporates and absorbs the heat from the air and food in the compartment. If the temperature produced by the evaporator is low enough, any moisture in the air around the evaporator will freeze and form a frosty coating on the coils. Here is the compressor, which acts much like a pump. It really has 2 jobs. It raises the pressure of the refrigerant gas, as we've seen, and in addition, it keeps the refrigerant circulating through the system. The inside of the compressor looks something like the inside of an automobile engine. It has cylinders, pistons, valves, connecting rods, and a crankshaft. An electric motor drives the compressor crankshaft. Usually, 2 or more cylinders are used for smoother operation and to keep an even flow of the refrigerant gas. From the compressor, the refrigerant goes to the condenser. Here, the warm, high-pressure refrigerant gas flows around a series of tubes. Cold seawater flows inside the tubes. The water absorbs heat from the gas, cooling the gas until it turns to liquid. Incidentally, as long as Freon is under pressure, it will liquefy even with the seawater found in the tropics, which may be as warm as 85 degrees. The liquid refrigerant then flows into the receiver or storage tank. It then flows back to the thermal expansion valve. Here, the cycle begins all over again. Gauges and controls are centrally located, so the operator can readily check the operation of the system. Although the system is automatic, no machine ever ran itself without some attention. Here, a glance at these gauges tells exactly what is going on. So you see, the key to modern mechanical refrigeration is latent heat, and the part it plays in changing a liquid to a gas and back to a liquid again. Once you know and understand this story, you'll know what you're doing when you're operating this equipment.
So, as we have seen, the refrigerant Freon expands and evaporates, absorbing its latent heat of evaporation and turning to gas. It is then compressed and cooled, gives up its latent heat of condensation, and turns to liquid. It goes back to the receiver and on to the thermal expansion valve to complete the refrigeration cycle. The cycle then repeats itself over and over again. When you know what the refrigeration cycle is, you have a good basis for understanding mechanical refrigeration.